Hello. In this video, we would like to determine the commutator for the lifetime function, t, and the energy operator, e. One thing to keep in mind, in this particular case, we can think of the time operator as being, for example, the lifetime of a particle, and the e operator as being the energy of that particular particle. And the particular form we're using for the energy operator here is not the usual one that we use in the time-independent Schrödinger equation, where we use the Hamiltonian operator, the h with a little hat on top. In this case, we're using the time-dependent function. So in the case of time dependence, the form that we use for the quantum mechanical energy operator is going to be h bar over I d dt. So let's determine what the commutator is going to be. So recall that by the definition of the commutator, it's going to be the first function acting on the second, and then the second operator acting on the first operator. And as we've done previously, we can simply insert a dummy wave function here just to make it easier to keep track of exactly on what the operators are acting. Another thing to keep in mind is, in this particular case, that our wave function psi is a function of time. So, what do we get? Well, remember, when we have an operator, a series of operators acting on a function, the operators proceed from right to left. So let's just bring down the t operator and have the e operator act upon psi. So what do we get? Well, we get h bar over I times d dt of psi. So we have the first derivative with respect to time. And that's what we've done is just simply have the nearest operator, the rightmost operator, act first. What do we get for the second side? Well, we're just going to bring over the E energy operator and have the T operator act upon psi. Well, by definition, the way that we interpret the T operator is simply to multiply by the time T. And that's going to multiply the wave function psi. So now that we've operated with the first operator, we can proceed with the next operator. In this particular case, the t operator simply multiplies by t. It doesn't act directly upon the constant, so we can pull the constant straight through. So we get h bar over I times t times the first derivative of psi with respect to time. Now for the next, we need the energy operator to act upon t psi. And this has the value of h bar over I. And it's the first derivative with respect to time of this product, t times psi. One thing which you'll notice is whenever we have a commutator problem, and it turns out that the commutator is not equal to 0, which means that the two operators do not commute, the reason mathematically that they do not commute is that at some point in this calculation, we take the derivative of the product. So if you end up having to apply the product rule, that's a hint, a very strong hint, that the commutator will not be 0 and the two operators will not commute. We can factor out h bar over I here. T times the first derivative of psi with respect to time. And now we have to apply the product rule. So we have the first times the derivative of the second, plus the second times the derivative of the first. So the first function is t, And we're taking the derivative of the second function, which is psi. So we get d dt of psi plus the second, and plus we have to multiply minus 1 in front. This gives us the minus sign. So we have the second function, psi, times the derivative of the first. So we take the first derivative with respect to time of time. So we get dt dt. And right away we can do a good deal of simplification. T times the first derivative of psi with respect to time minus t times the first derivative with respect to time. These add to 0, so they cancel out. We also know from the rules of calculus that dt dt is simply equal to 1. So we are left with minus 1 times h bar over I times our wave function psi. Now again, recall that we simply added the wave function psi to give some dummy function on which our operators could operate. So that's not an essential part of the problem. So the actual commutator is going to be h bar minus h bar over I. Now let me show one thing here which will allow for compatibility of other textbooks. In other books, this is not the final form of the commutator. What they tend to do is to multiply both numerator and denominator by I. Similar to the idea of rationalization of a fraction. Well, what do we get if we do that? The denominator is going to be I squared, and the numerator is going to be minus I h bar. Well, what does I squared equal? I squared is equal to minus 1. So if we interpret that value as minus 1, we can simplify the entire expression to be I times h bar. So if you look in particularly some older textbooks, it will list the commutator. Wherever we tend to use minus h bar over I, it tends to use the expression I h bar, and this shows that those two expressions are exactly equivalent. Finally, what does this tell us? That the commutator is not equal to 0. Well, since this value is not equal to 0, it tells us that the two operators do not commute. Therefore, we cannot simultaneously know the lifetime of a particle and its energy to infinite precision. This is another example where the Heisenberg uncertainty principle will apply. So whenever we're doing a commutator problem, the important thing is the commutator equal to 0 or isn't it? If the commutator is equal to 0, then we can simultaneously know both of the observables to infinite precision. If the commutator is not equal to 0, that tells us that the operators do not commute. Therefore, we are limited in our ability to know the uncertainties in the two observables simultaneously by the Heisenberg uncertainty principle. I thank you very much for your attention. Have a good one.